Welcome everyone here to the Linux Foundation Energy Project EVerest webinar about how EVerest can help you to simplify charging use cases. And my name is Marco. I'm one of the founders from the company PIONIX. And Cornelius, you want to?
Yeah, I'm Cornelius. I'm also one of the founders of PIONIX.
And we are your hosts tonight. And yeah, let's get into this. We are a public open source ecosystem project. That means in theory, he could be competitors within our audience. So antitrust policy, I have to show that for some seconds. So don't do bad things, basically, but we are happy to collaborate across industry. So let's dive right into this. So first, a quick non-tech introduction. What are we doing here and why are we doing this? So basically, if you look on the electric vehicle charging infrastructure out there, they all look really, really different from the outside. And even worse, they're very different from the inside. So everyone is developing their own software stack, even though I guess most of you just want to make one detail different, and everything else you're fighting with the exact same standards and anyone else in the industry, which is waste of a lot of money. And it's also breaks a lot of usability for all of our customers. And if we want to rock this electrification of transportation, then every one of us has to get a great user experience. So that's what we're here for. We want to harmonize all this under the hood. Also, the problem is you can argue like, okay, let's make a new standard. And this new standard is awesome. And then we have solved everything. Yeah, but if you're adding a new standard, what typically turns out is then you're having more standards everyone has to support. So things don't get better. They're just getting even worse. So we are not here to create a new standard. We're here to implementing all the existing standard in one shared cross-industry code base. Yeah, and still we want to do it in a way that everyone from you can differentiate and building awesome products, and it don't have to look the same for all our customers. We're quite good already in creating ecosystem around this. So this is not a complete picture, but let's say the project EVerest is part of the Linux Foundation, which is great. They're doing supervision, they're doing quality assurance, networking, whatever. I'm coming from PIONIX. We started this project. So far, donated most of the code. There's big code donation preparation ongoing. We have a lot of universities now joining this. We have a lot of different hacker communities where we're actively advertising this. And yeah, the EV charging supply chain with Phytech, Texas Instruments, ChargeByte already on board. There are charging stations to be EVerestified from ChargeByte, FoodTech, and Male. And we're also having a lot of collaboration with different charging cloud solutions. This list is far from complete. I think currently our libOCPP has more than 20 or more than 30 different clouds already tested. And there's, with commercial NDA covered, a lot of more going on under the radar of the slides. Yeah, but what EVerest actually is, I will hand over to Cornelius.
Yeah, so let's have a closer look on what EVerest actually is. EVerest is a software stack that runs on the EV charging stations. So most of the charging stations that you find out there, maybe except the very cheap ones that you use at home, typically already run Linux. And the typical components that you will find inside is, if you look at the lower left, there is some sort of power path electronics. That's essentially all the switching and RCD and all that stuff. And then there is a higher level control unit, which is often a Linux board. And on top of that, you will find displays, RFID readers, and other components. And EVerest is the software stack that runs on this Linux board that makes the charger smart, that talks to the car for charging, that manages payment, that manages energy management, and that does all the display rendering and all that stuff. Yeah, next slide. So it has all the features that you would expect from a charging software. So it's not just a single protocol or a bunch of single protocols, but it's really a complete seamless software stack with all the protocols and all the, let's say, glue code in between. So it's made very seamless and all the modules fit together very well. We'll see that later on as well. The features that are implemented is the basic charging according to IEC 61851. That's the basic PWM charging that you mostly see in AC. It does support ISO 15118-2 and DIN spec 7121 for DC charging, and the ISO is also supported for AC charging. So it does support the high-level charging as well. And of course, it also implements Slack protocol for that. It speaks OCPP 1.6 JSON to the cloud backends. And one of the cool features here is that we really implement all the optional profiles as well. If you read through the OCPP standard, you will find that a lot of functionality is marked actually optional, and many implementations out there only implement the core profile actually. But we try to support really all the features that OCPP 1.6 offers, as well as all the additions and backports that are coming up right now. For example, security extensions, or we will also support plug and charge on 1.6. We do support auto charge right now. Plug and charge is coming up, as I said. We also support multiple authentication sources. So you can have OCPP, but you can have also local authentication sources in parallel, as well as all the system management via OCPP. So reboots, collecting log files, and all these functionality. Yeah, so for external devices, we do have an external API. We do support a lot of hardware devices on Sunspec and Modbus, such as power meters or isolation monitoring devices. EVerest comes with basic energy management right now. That's already included. It includes also a display app based on Flutter that you can use, that you see on the lower right, actually. And it also comes with software in the loop. We will talk about that in a minute. For next year's, we plan to support also OCPP 2.01, as well as the new ISO 15118-20. We will upgrade the energy management quite a bit to support also grid-based protocols such as IEEE 2030.5 or ADR or EEBus. That's on the roadmap. So next slide, Marco. So why would you choose EVerest now if you're trying to build a charging station? One of the first questions that you usually ask is like, which component do I have to write myself and which can I basically buy anywhere? And we really think you should have both. So let's look at this first. If you're making your software modules yourself, there's of course the biggest benefit that you're super flexible because you have designed everything, you wrote all the code, so you can do whatever you want with it. But also it comes with a lot of disadvantages, such as you have really high engineering costs, you have a long learning curve, you have basically no benefits of scale because you're reinventing the wheel. If you buy components, and there's a lot of software stacks out there that you can buy for EV charging, that of course gives you some price benefits at scale because they do it for multiple customers, and it's also a proven system that's out there, and you know it's stable. But also it gives you some sort of vendor lock-in, and typically you can't change anything. You get these black box libraries. So what you really want is to get the advantages of both the make and the buy approach, and this is actually what you can get with open source. You get the best of both worlds. So let's look at that. Like in a typical implementation that we've seen on chargers, and in the left is basically you start with some proprietary hardware boards that you buy somewhere. They usually come with an open source Linux board support package, but already there you have a little bit limited control because it's comes from the manufacturer of that board, so you can change it a bit, but you're still dependent of the board manufacturers. And then you're buying some protocols like ISO 15118 from some company, maybe OCPP from another company, which are basically black box without any control. And then on top of that, you create your proprietary charging software where you're again reinventing the wheel because a lot of other companies did that already. If you do it with the Linux Foundation's EVerest, you can start basically with hardware reference design. Those will be available actually soon, completely open as well. You get a Linux on top of these designs that you can fully control because you can create your own hardware with the help of the reference design. You can use EVerest. You have full control over that. It's completely open source under the Apache license. And you can build just the USP features that you need on top of it. So all your development power, you can really focus on the few USPs that you really have, but all the stack below is basically there already. So you have full control over the full stack, but you can also get commercial support for any of these stacks. There's multiple providers now that give commercial support for EVerest in the stack. So you can basically choose where you need help or where you can just use it as it is and do it yourself. So you have all the control and all the support. So next slide. One really cool thing about EVerest is it really has a really beautiful modular architecture. So I will show you the EVerest framework a bit. In most of the implementations that we have seen that are on chargers right now in the market, you have a situation that you have multiple software stacks that you bought from different sources. And there's usually some glue code in between because they're not really compatible and they're not really made to work with each other. And we basically designed this from scratch. And we started with the framework, what we call the framework. It's basically a microservice architecture. So EVerest is split up in several modules. You will see that also later. And these modules can communicate. They can call commands of another module. So module B can call a command from module A, or module A can basically publish an asynchronous event that module B receives. And this is typically done with something like MQTT or dbus, and we chose MQTT, and each of the microservices module runs as a separate Linux process. So next slide. MQTT is actually a quite popular choice in the EV charging industry. A lot of the stacks out there already use MQTT. And what you typically see is that it comes with some sort of documentation. It might be a PDF or even an Excel sheet, basically specifying which MQTT topic does what. So it describes like, okay, you need to publish true on this to, I don't know, pause the charging, or it describes like how the data looks like that you can subscribe to. But this comes with a lot of problems because what if you require multiple instances of one module, for example? Then you already get clashes on the MQTT topics. Of course, you can solve that with prefixes and stuff like that. But you're running into a lot more issues in the long run. So what if a module path, like a topic path, changes on the MQTT? You need to update that in all of the different modules that use this topic. And it's sometimes really hard to find that in the code because you don't get compile errors or anything for that. So we started off with another idea and said, okay, let's have an abstract description first of what a module is, what it provides, what the interfaces are, and what the dependencies are. Like module A does require another module to work, for example. And we do this in YAML. So there's YAML descriptions for modules, for the interfaces and everything. So we get, first of all, compile time errors if something changes, for example, and it's very easy to maintain, but you also get things like automatic dependency checking at boot. So you can actually see if your configuration that you make is complete and now the requirements are fulfilled. And there's also a graphical configuration tool to wire these configurations together. I will show you that in a minute. And it's also used to generate the human readable documentation out of that. One really cool thing is it also comes with type support for C++. So all the data structures that you define in the YAML on the interface between the modules will automatically be compiled into real C++ types. So you get all the compile time type safety that you would expect from C++. One interesting feature, we will see that later in the application, is also that this can spread over multiple computers or chargers. Since it's MQTT, you only need a network connection in between. So the EVerest, and with all its modules, it does not only run on a single charger, but you can also regard this as EVerest being spread over a whole charging part. We will see this in a minute. Next slide. Yeah, we'll basically skip that. Go to the next slide. So what I will show you now is how to configure EVerest for an AC charger. So basically how to build an AC charger in just 2 minutes, because it's super easy, and how well all these seamless building blocks really fit together. So this is our graphical configuration tool that you can use to configure EVerest, and you will start off with the EVSE manager, which is kind of the module that manages one charging port, so one outlet to the car. And the first other module it needs is actually a hardware driver. So we're adding the Yeti driver here, which is one of the open source dev boards. It needs energy to charge a car. So we just add the very simple configuration here with just one energy manager and nothing in between. That supplies energy for that charging port. We do want this to be a high-level charger, so we're adding basically an ISO 15118-2 protocol stack here that attaches to this central EVSE charging module. And for ISO communication, you also need the Slack protocol. So we connect a Slack module here as well that does the physical link setup according to ISO 15118-3. And maybe you don't want your charger to be free, so you need authentication. So you're adding an authentication manager here. And this now requires two things. It needs a source, so something that spits out tokens, basically. We're adding an RFID driver here for a very popular chip, the PN532. And basically, whenever you swipe your RFID card now on the reader, this will basically give out the RFID tag ID into the auth manager. The next thing that we'll need is the authentication manager. We need to find out if this tag is valid or not. So it needs some source of validation. We're adding OCPP here. So basically what happens now, you swipe your RFID card, the tag goes to the auth manager, is being sent to the cloud for verification, and the answer is being sent back. And then the auth manager can basically start the charging session in the EVSE manager. What else do we need? We need a system module that does things like reboot or log files collections for the OCPP protocol. We want to have a small API that we use, for example, to connect the display application on the charger. And then essentially we're done. So this is a complete smart AC charger with ISO protocol and with OCPP. Let's go to the next slide. Yeah, and we're basically ready to go, and we can just start EVerest in that configuration. So we wired all the modules together. When we started, it will also check that all the necessary connections are being made. You can see that some of them are still open, and this is because some of them are optional. You don't need to connect everything. And in the YAML files, the system knows which one needs to be connected and which are optional. Now, this was a very simple use case for, let's say, a public or semi-public AC charger with just one charging port. So the true beauty of this modular approach, you can only see if we go to slightly more complex applications. So on the next slide, you can see in the lower right, I added basically another EVSE manager and another protocol stack and all that sort. And just as an example, I added a second DC charging port here. So it's essentially the same as before, but now you have a charging station that has one DC output and one AC output. And both of these charging ports actually share the same energy manager. So they're connected to the same output of the energy manager, which means the energy manager will automatically do load balancing for those two ports because it has only one output. A similar thing actually happens totally automatic on the authentication manager, because both of the EVSE managers, it's a little hard to see, but they are both connected to the same auth0 node here, which means you have only one RFID reader and one auth manager, but this manages now both of the charging ports. And you can, for example, on the display, select which one you want to enable and stuff like that. Same is true for the OCPP. There's only one module here. So in the backend, this will now show up as one charger with two outlets, basically, with two connectors to cars. You could also wire up the same thing a little bit different. And for example, say I'm loading the OCPP module twice and connect each one to one of the EVerest managers, and then it will show up as 2 chargers having 1 outlet in the backend. So all of this can be configured without changing a single line of code, just graphically by arranging the modules and connecting it the way you want it to be. So next slide. Another application that's a little bit similar is, imagine you're having a big charging park. There's just 2 chargers here shown here, but it could be like 50 or so. And you're having a centralized payment terminal in the middle. So basically you plug in your car and you walk to that extra payment terminal, do your payment with whatever method there is, to select, for example, charger 2 in that case. And the charging stations are all connected via network or Ethernet or Wi-Fi, and EVerest can do remote connections between the modules. So on the payment terminal, it's a separate piece of hardware. You will just run a small EVerest with the authentication manager, maybe OCPP, and the RFID driver, but it doesn't run actually any charging stack on that because it's just a payment terminal. And on the individual charging stations, you will just run the charging stack with all the protocols, and the EVerest manager will be remotely connected to the auth manager. And even that you can do without changing like a single line of code anywhere. And this is one example where EVerest kind of runs on the whole charging park spread over multiple devices here. Next slide. Quite similar, actually. You will probably even have both of them combined in many applications, which is no problem, is centralized energy management. So in the very first example, I showed you that sharing the energy manager between 2 ports already does load balancing of these 2 ports within a single charging stations, but you can use the exact same method actually to do load balancing between individual charging stations in a park, for example. And what is shown here, just as an example, is you're having 4 EVerest managers, so 4 individual outlets to cars, and there's 4 cars connected, and each of them have different charging goals. So for example, the first one needs to leave 7 a.m. in the morning, and the user entered this on the display, while the second one, for example, only wants to charge solar excess energy, if it's, for example, in a house with solar panels on the roof. Another one will need to leave as fast as possible. So he wants to charge as fast as possible, obviously. And there's maybe another application where you only want to charge if it drops below a certain price limit. So in many areas in the world, there's no varying prices. So you get new prices every hour, basically, depending on grid load and renewable energy stuff. So the stuff on the left where you see energy manager and all the fuses, this basically represents the power grid of that charging park or of that house, and it basically works the same way as before. In the diagrams earlier, we basically represented the internals of one charging box, like what hardware is built inside, like an RFID readers or something. And the same methods you can use to basically model the outside world of the chargers as well. So if you start on the left, there is basically the energy manager that manages the whole tree that comes. And right next to it, there's the grid fuse, which says 22 amps. That's a little low for a typical house connection. But anyway, it's just an example. This is basically where the grid is connected. And here already we're feeding in price information. This can be constant pricing, but it can also be varying with every hour. And it's also different for both directions. So it can also specify like, okay, if I draw power from the grid, it's 30 cents per kilowatt hours. But if we're inject into the grid, it's maybe just 8 cents or something that I get. At this point, typically there's also a power meter connected. So we connect the power meter driver module here as well, so that EVerest knows how much power is flowing here at that point. If you go further to the right, you see the fuses that distribute the energy to the actual charging stations. And what's really cool here is we can, this tree can be arbitrarily complex, so you can add as many layers as you want. It just needs to represent like the real wiring on site. and the energy manager on the left will actually make sure that none of the fuses in that tree ever blows, as well as trying to optimize energy in a way that all the different charging goals here are fulfilled as good as possible. So this is a very advanced energy management. Actually, what you see typically in the market is just a, let's say, a simple master-slave concept or something, where one box basically has a limit of, let's say, 32 amps, and it just distributes that to multiple boxes. But here you can do this really over a whole tree with fuses at different levels, which is far more complex. You can also include power sources here because it's prepared to be bidirectional anyway. So for example, if you have solar on the roof, you can add a solar driver here, which will basically feed energy into that tree at a specific point. And also with the upcoming 1511.8-20, the cars will also actually be bidirectional, so there will be both a power source and sink. And then we can do really interesting optimizations. For example, the car that needs to leave as far as possible, like as fast as possible, can actually draw energy from another car if the grid cannot supply that energy right now. Because this maybe parks longer time and we can recharge that after the other one already left or something. So then we can do a whole lot of new optimizations, which will be quite complex. So this is the complex stuff is what's coming next year. The basics are already implemented right now. Next slide. Yeah. One cool feature about EVerest is also the software in the loop simulation. So next slide. For all the modules that basically are hardware drivers or hardware abstraction layers, there is also simulated modules with the same functionality. So I just made an example on the right. This is essentially the same AC charger that we built in the very beginning, but now in a software in the loop environment. So if you look at the EVSE manager, which was kind of the central module managing the charging session and the actual charging logic, below you'll see an EVSE hardware simulator. So it's not a hardware driver anymore, but a simulated charging hardware, which then can connect to a simulated car. So we also have modules that simulate the car. And the car also actually supports ISO 15118. So you can do really high-level charging with the complete protocol just by arranging the modules here. It even simulates the slack between those two. And this is quite powerful. Now here it's a very simple application, but you can wire up, let's say, complete charging parks with hundreds of chargers and cars coming and going. You can control the simulated cars to plug in and plug out and even to do errors. You can make them short circuits or trigger RCD errors or whatever you want. And you can basically test all your scenarios purely in software on your laptop or in a Docker container that you push somewhere in the cloud and run like full simulations. We heavily use Node-RED here, which is a quite nice tool to do quick and dirty stuff. And this, for example, can be used to control the car simulations or see what they're actually doing. Yeah, so this is a feature that's also super helpful to get started, or actually we're doing most of the development in a software in the loop environment before we actually test it on real hardware and with real cars. Yeah, next slide. Yeah, EVerest is also well tested. That's also very important because we don't want this to be like just a hobby stack or just a scientific experiment. We really want this to be something that's usable in the industry, out in the field. So next slide. And how do we achieve that? We try to go really to all the testables for compatibility testing. So for example, we visit all the Charin testables to charge with different cars, also with the prototype cars, and work with the car manufacturers to ensure that we're really compatible to whatever they have before it even hits the road. We're doing a similar thing with OCPP, with the cloud backends. We try to test with as many commercial backends as we can get hold of, basically. And if you have a commercial backend that wasn't tested and you can organize a testing account, we're happy to do it and ensure that it's really compatible. We also go to the OCPP plugfests from the OCA, and we're using the official OCA test tool as well as our own EVerest automated test tools, which is even more powerful than the official OCA tool because it covers not only the happy path, but also all the error cases that can happen in an OCPP session. And something that we are preparing, but that's not working right now, is that we're basically doing fully automated application test cases, basically of scenarios that I showed you earlier, that we simulate the full charging parks with hundreds of charging sessions and stuff like that. We can do that already, but we're integrating that into automated tests so that basically on every commit, for example, you can run through 100 different applications and see if they're actually still working. We also get, of course, support from the Linux Foundation Energy in terms of code scanning and security audits. And we're following also the Open Source Security Foundation's best practices to make sure that the code is also secure. Yeah, one big feature of EVerest is also, while you can run everything in the software in the loop, there's also actually deeply integrated into many hardwares that are out there right now. And there are some hardware reference designs available and boards that you can buy to get started. Yeah, on the next slide, the typical requirements for EVerest hardware is you do need a Linux system. Like a really good choice is typically a single to dual core quad, maybe ARM core, maybe quad core if you do display and some animations on the display as well. But for EVerest alone, actually one core is enough, maybe around 1 gigahertz, maybe 1 gigabyte RAM or 2 if you do really advanced stuff, and let's say 4 gigabyte of flash. But these specifications are, let's say, nice to work with, but we can also run on like much lower hardware specs if that is really needed. And if the price pressure on the product is really there, then we can go with a lot less, because the basic functionality is all implemented in C++. We made it the decision so that the core functionality is really efficient. You can write modules in Python or JavaScript as well, but it's like all the core functionality that typically runs on the charger is C++, and the JavaScript and Python is more for testing and software in the loop simulation that you would run on more powerful hardware anyway. You can build such a board yourself, or maybe you have already one. It's also fairly easy to port because there's essentially just one module that the EAT driver, for example, that we used earlier, basically the module below the EVSE manager that you need to rewrite. It has a very simple interface. In principle, it's just PWM output that you somehow need to enable on your hardware and reading back the states from the car, like A, B, C, D, E, F, as well as you need to have a power line modem that's typically at the moment based on the QCA, for example, or the Lumicil, and those are already supported in EVerest. So maybe you need to port the RFID driver. It's not, if it's not one of the most commonly used chips that we already support. Boards that we do support out of the box, there's, for example, hardware available from ChargeByte that was formerly known as Intec. They have boards already running with EVerest, and that comes with EVerest pre-installed if you want. And on the next slide, there's also development kits upcoming from Texas Instruments and Phytech, which will be supported by EVerest when they are released early next year. There we also have a separate microcontroller that's in the CPU, and we also support like the firmware for that microcontroller. So EVerest is really deeply integrated on the hardware. It's not just the Linux process, but if the hardware has additional microcontrollers, we try to provide code for that as well. On the next slide, this is kind of the first development kit that is available. It's the PIONIX Belay box. This is basically what we use to start the development on. It's a high-level board, so the compute board based on a Raspberry Pi. So it was made to be really developer-friendly and not so much mass production-friendly, and comes with an AC power board as well. You can do DC with that as well. There will be a tutorial coming up soon how to build a DC charger with that hardware as well. And what's really cool about that one is that we will release like all the hardware as open source as well. So all the schematics, the layouts, everything, it's designed in KiCad. So it's even designed with open source software. So you can actually download that in probably 1 or 2 weeks from GitHub and just build your own boards if you want to, or buy like pre-populated ones and get running with EVerest. Yeah, so next slide. Yeah, that was basically it. So Marco, you're on mute.
There's one technical detail I want to add. First of all, thank you, Cornelius. It's always a pleasure to see this every time. So you showed so many, let's say, Lego building blocks. I think it's really important to say that you can add your own building blocks and you can also modify existing building blocks. So you're not restricted to what's there. There's basically no limit to what you can do with this.
True. Yeah.
You know, okay. So how to get in touch, how to get started. So we have a lot of upcoming events where one of the current members of this project will present. So I think today, that's already over, ChargeByte presented at China in India. We will be on the Consumer Electronics Show in Las Vegas. We will be on the FOSDEM in Brussels. And by the way, I think for the next 2 weeks, you still have the option to submit your own contribution to that conference, becoming a speaker, becoming a contributor. So if you're interested in that, please reach out to us. And you can see the list here. There's a lot of stuff just for the next 6 months upcoming. Besides that, we have a GitHub repository. Please check it out. There's a mailing list. So if you have any technical question, please go on that mailing list. And also, we know the documentation isn't perfect yet, but we're investing quite heavily in getting that up to a really good shape. So if you're missing anything or you can't get started immediately, just ping us on that mailing list. Someone will answer you and help you to get into this. We have a technical steering committee, which is about once a month, where we typically give high-level update, what's new on the project. That will also be recorded and on YouTube afterwards, so you can see what's going on the high levels, what's new, our changelog. We have a weekly tech sync where we're really discussing architecture decision in detail, where we looking into what's missing for a certain pull request, how to get that moving. It's also public, you can join that. The invites and the login data for all those events is basically on the mailing list, so if you subscribe to it, you will get informed. You can find us on Twitter. You can find PIONIX on LinkedIn. There's currently no EVerest LinkedIn account. Yeah, and please reach out to us. So, and that's basically it. And we're happy to open the stage for discussion. And yeah, thank you for your attention. And I think we already have a couple of questions on the Q&A module. So let's maybe go through that. First one, Cornelius, I will just ask you, playing the advocate of the audience. Is there a specific timeline for ISO 15118-20?
Yeah, that's a question we're actually hearing quite often. So let's say our timeline says that we should have that running by next summer. It's hard to specify an exact date because we don't have a test target on the other side at the moment. So we do not have access to a car that really implements that in real life. Of course, we can test against protocol testers, but also history tells us that testing against protocol testers is a different thing than testing against a real car. So I guess we'll have an implementation that will be working in summer, but I'm sure it will also get a lot of updates later if more cars actually support the -20.
Okay. Next question. Will there be the slides available for download afterwards? I can answer that. So we'll put them in the YouTube description, a download link. We'll put the slides in our EVerest mailing list, which is list.lfenergy.org/g/EVerest. So again, lists.lfenergy.org/g/Everest. Also put it into the chat, the URL, so everyone can copy that out. So if you have more questions, please feel free to put it in here. And you can also raise your hand in the chat section, so we can also kind of talk to you directly now. Until then, basically coming up with my own question. So what is about OCPP 2.0?
Yeah, that's also something that we're planning for next year. We think it's super important to have that because it does contain a lot of new features that are very important. But we also see that the industry is relatively slow in adopting 2.0. So many of the backends actually support only 1.6 as of now. So we truly believe that even for the next couple of years, that we actually need to have kind of a dual stack solution where you can basically just drop in a 1.6 module or drop in a 2.0 module, depending on which backend you're talking to. And this is also why we said, okay, we really want to have all the features in 1.6 really complete as well, and not just say, okay, plug and charge will come in 2.0. It will also come as a backport in 1.6, and we'll always try to support both there.
Maybe another related question we often got asked is, so there is some Java in the repository. Why is it so? And is there any change to that?
Yes, so that's also one question, because on embedded systems, actually, everybody wants to get rid of a Java dependency. We do have a Java dependency basically in one spot right now. That's the ISO 15118-20 implementation. We have actually two implementations there that are both open source, but both have a Java dependency for the XC codec. So ChargeByte will actually donate like a new XC codec and will basically write a new complete 15118-2 and -20 implementation that's purely C or C++. And this is what we will use to basically replace the Java dependency here on embedded systems.
And so far I heard from our ChargeByte friends, it might be in the next 2-3 weeks that this goes live. And I think what is really awesome on this, it's not just parser for XC codec, or it's also a generator for a parser. So basically, if you come up with your own extensions to the protocol, or if you have certain cars which kind of mess up the protocol, you can include your own schematas and generate an alternative parser. So
yeah,
this is totally new to the entire industry. So
yeah, or actually fix bugs. So maybe someone on the call actually uses the OpenV2G, the old Siemens XC stack that was also written in C, and that actually is auto-generated code, and it was also open source, but they never open sourced the auto-generator itself. So whenever you needed to fix bugs, you need to do that actually in auto-generated code, which is not what you want. So we're trying to do it a lot better here and to be like truly open, so that everybody can use it and also everybody can really contribute. So we're happy for everybody who helps us in any way.
By the way, truly open. Let's define that. What does it mean for us?
Yeah, truly open, that things are really completely open source. So we don't want to have this solution where you have like parts of the software are open source, but if you really want to use it, you need to buy that commercial plugin here to make it actually work. But for us, it's really important that the Linux Foundation project here is something that's available under the Apache 2 license. So anyone can really use it. It's complete. There are no hidden commercial modules that you need to add to make it work. You can also use it commercially because of the Apache license, so it's not infecting anything. And really anyone anyone can really contribute to that as well. So it should be a community effort and not something of a single company that does it.
Yeah, and actually, what does it mean to being non-infective? I think this is really important for an industrial project. So if you're adding or if you're changing a line of code, and this line of code is a company secret, you don't have to donate that change back. You don't have to donate anything back. So whatever you think it's appropriate for you, just add it to the project on your copy and you can keep it. And if you think there's a worth for you, we're happy to take in any changes as soon as someone looked at it and it's a certain quality. But we are super happy to both, if you keep things private for yourself, to have a competitive advantage for your project, or if you donate it back to the project. So I think, yeah, next question.
There was another one dropping in the chat. Maybe you want to catch that up?
Yeah. So currently in place so what support is currently in place for charging network managers for implementation and use of EVerest North America? So charging network managers for implementation. Not sure what you mean with that. EVerest in North America, I think there's no limitation. So we have been on those plug fests as well. Maybe you can, I think we should be able to, if you put the raise your hand button, we should be able to put you on speaker if you like.
Yeah, what?
Okay, can you hear me?
Yeah,
yes.
okay.
All right, sounds good. Yeah, thanks for that really interesting presentation. Yeah, this question is mostly in terms of what are the tools available for a charging network manager? We're talking about those that exist currently in Canada or the US. If they're looking to implement and use EVerest, what's the support like for the actual use of the programming?
So
is everything done remotely, for instance, or do you have staff available to walk project implementation managers or technologies through with the network managers?
So it will basically need to be implemented by the charging station manufacturer. So if you're having a huge network and you're, I don't know, you bought your charging stations for manufacturer A, you basically will need to approach the charging stations manufacturer and ask them and say, hey, I want the charging stations to run EVerest because then I can drop in additional features that I wanted or something. So the charging manufacturer that basically builds the hardware will need to work with EVerest to port it to this hardware.
Yeah, and to extend on that, so basically you have seen we're working with a lot of different vendors in this industry on the supply chain of those charging station vendors. So let's say we can maybe put motivation on them from both ends, once from the supply chain and once from the demand chain. And also this would enable you as a station operator, for example, if you have vendor A and vendor B and you want to have your own user interface, you can write that once and including it for both vendors. So you can come a bit more independent of them on the long term. Mm-hmm. And you don't have to spec out a user interface as a drawing and then hope everyone implements it right.
It may also be that the charging manufacturer, like most of the charging station manufacturers, they don't actually build all the components. So for example, they're buying like a charge controller and just mount it within their case. And it may already be that the charging controller is already supported by EVerest. That may also be the case. So it depends on which one they buy to build their boxes.
No, that's very helpful. So essentially the OEMs would be the ones responsible for the programming from the get-go, and then it's up to the I guess the network operators to ensure there's that connectivity with their back end. But that's where they can probably connect your network as well to ensure that they're getting the support they need for that connection to take place.
No, we don't have a back end. So maybe let me show you the.
We can basically connect to any backend that's already out there as long as it supports OCPP. And even if it doesn't, it's fairly easy to implement like new protocols as well.
Okay.
So if you go on github.everest/libocpp, there's already a list of charging stations we tested, so charging station management system, like the backends we tested so far. And this list is far from complete. So there's actually more to it already. So we have been last week on a big festival in the Netherlands, and I think added 10-ish to this list, maybe 15. And yeah, at the moment, this comes typically without any big problems. And if there's a problem, this is something we as PIONIX happily take care of.
All right, wonderful. Thank you so much.
Thank you as well. Maybe to extend on that, so the business model from PIONIX, because that's often asked, so why are we donating that for free? We are basically supporting you on top of that open source stack. So if you want to have a change, if you want to have, let's say, a maintenance contract that you get every month, narrowly really tested software update where no bugs are included and runs on your hardware, we take care of that. So we're not selling the software, but if you need any additional services, we are here to help.
Yeah, we actually have one more question from Martin. He's asking whether there's an example on how low the hardware requirements can be, just to get the very basic stuff running. Yeah, that's also a good question. We actually didn't make experiments on how low we can go, but if you're not using the, let's say, modules that, for example, render display content or something, but really just the charging stack and maybe the OCPP, then literally any ARM should do, even if it's like an ARM 7 or 6, or even with like, I don't know, 128 megabytes of RAM, that actually should be possible to run the core at least on that easily. What we don't support right now is anything that doesn't run Linux. So all the microcontrollers that run things like an RTOS, like FreeRTOS or something, or even bare metal, that we don't support. But that's maybe also interesting to mention is that a lot of the functionality of EVerest is actually implemented in a C or C++ library. And then there's a kind of a wrapper module that integrates it into EVerest. And at least the libraries you could, in principle, also reuse on microcontrollers even.
Then that's kind of half a question. I've seen that here some people from a battery management company. Maybe to extend on that, EVerest is not yet like a home energy management system, but it's not far from this. I mean, if you remove, let's say, the APIs to the cars, you basically can manage locally the energy and locally batteries. You have seen the slide on energy management. Yeah. So this is something on the very, very far roadmap as well.
Yeah, and but I guess this will also happen kind of automatically over time, because I'm sure we will have drivers for that energy interface, for example, for heat pumps, for the heating of houses or something, because like all big consumers that could potentially interfere with charging at home, for example, will probably get some drivers implemented so that it kind of will turn into an energy management system as well. But what's important to understand is you can use, let's say, this EVerest included energy management systems, but we will also build bridges so that kind of EVerest acts as a follower, as a slave to other energy management systems. That's also something that we're planning to do.
Basically, with OCPP, we're already doing that.
Yeah, true. Yeah, but you can also combine that. Actually, if you're setting limits via OCPP, even via smart charging, you can basically use those limits within the energy management and still do like local energy management in parallel with the OCPP.
So, are there more questions in the audience? So, if not, I'm happy to see you in our next webinar. We will announce it again over our mailing list and over social media. I think maybe, I'm not sure if we do it right before Christmas, so probably first, let's say early next year, let's see. And we will dive into more specific topics like OCPP in detail, how does it work, ISO 15118 and the DIN spec charting norm, how do they work in detail. So we have experts for a lot of those topics in our team who have a really, really broad team, and we're happy to really make the deep dives in those topics as well. And yeah, then thanks a lot. Hope to see you soon, and take care of yourself.